Okay, so we're on to series lecture 15. I just thought I'd do some examples. So far we've got geometric series, we've got the integral test, we've got the comparison test, and the limit comparison test. I wanted to do some examples here. So this one here, this first one, well, how would I work that? That's not quite a geometric series as written, but you might notice that in fact it does break up into 1 over 4 to the k plus 3 to the k over 4 to the k. And both of these separately are geometric series that converge. And remember, if they converge, you can write them as the sum of what they converge. Then you can write it as the sum of the series. Be careful, if they don't converge, you can't do that. But since both of these converge, the sum of them converges. And so this converges. Geometric series. In fact, we know what it converges to depending on what we start with. You know, if we're starting with 0, this is going to converge, this one will converge to 1 over 1 minus 1/4, and this one will converge to 1 over 1 minus 3/4. If we're starting with 1 or 2, we'd have to tweak that a little bit. Now, this one can't be broken up, but it does look like we should be able to compare it to something. It looks like we can compare it to 4/3 to the k, and in fact we can use the straightforward comparison test here. Well, no, we can't, because 4/3 to the k is going to diverge, and this is less than 4/3 of the k, so we're going to use the limit comparison test here. Limit k goes to infinity of 4 to the k over 1 plus 3 to the k over 4 to the k over 3 to the k, and that simplifies to the limit k goes to infinity of the 4 to the k's cancel. I get 3 to the k over 1 plus 3 to the k. And you might notice that the 3 to the k takes over from the 1 plus 3 to the k, but let's just use L'Hopital's rule because that is of the form infinity over infinity. Limit k goes to infinity of 3 to the k ln 3. Derivative of 1 is just 1, 3 to the k ln 3, and of course that's just 1. Okay, so either they both converge or both diverge, since this thing here, 4 to the k over 3 to the k, diverges. This one over here diverges. Okay, so we've got that one, and now let's look at this other one. It's hard to say what to compare that to, right? So this might be, actually, this looks like it might be a good integral test one, because I think I could take the integral of 1 over x ln x, and let's just make sure it's in the right form. 1 over x ln x is going to be positive, definitely continuous for x bigger than 0. Bigger than 1, actually. For x bigger than 1, I've got to start with something bigger than 1 here. N equals 2 and 2 infinity or something. And it's going to be decreasing because the denominator is going to be getting bigger and bigger, so it's going to be decreasing. So this is a good thing for the integral test. So let's go from, let's not go from 1 to infinity, let's go from 2 to infinity, because we already know it's not defined at 1. I didn't put the limits on. The limits are wherever it starts making sense. So this is going to be the limit as t goes to infinity of the integral from 2 to t of dx over x ln x. And I said that was doable. Why is that doable? What would you use? U substitution, right? U equal ln x. And then du is going to be 1 over x dx, right? So I get this is limit t goes to infinity, so the endpoints when x equals 2, u is equal to ln of 2 and ln of t, and that's going to be du over u, right? Which is the limit as t goes to infinity of ln u from ln2 to ln t, which is the limit as t goes to infinity of ln of t minus ln of 2. Sorry about that, going down the side of the page there. Even on this, I go down the side of the page. But actually, all we need to know is whether this converges or diverges. And ln of t goes to infinity, and ln of t then is going to go to infinity. So this diverges. This diverges. So that means this thing over here diverges as well. Okay, so there's an integral test one. That's a little bit weird, right? Because it's like, remember with the p series, n raised to any power bigger than 1 is going to be a convergent series, 1 over n raised to any power. But what we're saying is n times ln n is somehow smaller than n raised to any power bigger than 1, even 1.1 or 1.2 or something like that. That's sort of an odd one. Okay, so let's look at this thing here. E to the 1 over n over n. What can we do with that one? Well, what I notice is that e to the 1 over n, that's always bigger than e to the 0, right, which is bigger than 1. So that means e to the 1 over n is going to be bigger than 1 over n. And that's, well, this one diverges, right? So since this is bigger, this has got to diverge as well. This is one where the limit comparison test may not be that good, because at e to the, maybe it would. E to the 1 over n, and actually it would be. That would go to 1. The limit comparison would work there, but the regular comparison works. And this last one is one where the limit comparison doesn't work. The reason the limit comparison doesn't work is because it's really hard. I mean, if we compare it to any series we know, 1 over n factorial is going to say, like, if I try to compare it to 1 over n, I'm going to get a limit of, let's just look at that, 1 over n factorial over 1 over n. That simplifies to n over n factorial, which is 1 over n minus 1 factorial, right? And really, it's not a geometric series. If I compare it to any p series, I'm not really going to get a finite. This is going to 0, right? Everything I compare it to with the limit comparison test is going to give me an issue. However, it's pretty easy to use so let's erase this one. It's pretty easy to use the comparison test on that one. So let's use the comparison test. And what do we want to compare it to? Well, remember, 1 over n factorial is equal to 1 over n times n minus 1 times n minus 2, ... When I multiply by these all the way down to 1, right? So these are all bigger than 1. When I multiply things by bigger numbers, I'm just getting bigger numbers. So this is all going to be bigger than 1 over n times n, less than. That's all going to be less than 1 over n minus 1. Let's say less than or equal to, as long as n is bigger than 2. So as long as you're going from 2 on, we've got this less than that. Less than or equal to that. And we really only care starting some finite place out. That's all that matters. So I'm going to compare it to this thing. Now this thing is not a p series or a geometric series either. However, this one is comparable to a p series, right? What p series, let me rewrite this. This is going to be 1 over n squared minus n. And 1 over n squared minus n is not less than 1 over n squared, but it's comparable to 1 over n squared. Let's use the limit comparison test here. Limit n goes to infinity of 1 over n squared divided by 1 over n squared minus n. It's going to be limit as n goes to infinity of n squared minus n over n squared, and that limit is equal to 1, which is non-zero and finite. So this series here converges And this series is less than that, therefore this converges as well. So we had to use a combination there. We had to use the comparison test to get it less than something that we could use the limit comparison test on. Why didn't I say it was just less than 1 over n? Well, because 1 over n diverges, and saying it's less than 1 over n isn't enough to, it doesn't tell us anything. Okay, good place to stop.